physics is enabling it to happen. We are telling the physics what to do, and the physics does what we tell it to do. The physics isn't deciding anything.
Most physicists would say that everything reduces to particles obeying fundamental laws. Professor George Ellis, who co-authored with Stephen Hawking singularity theorems, which extended Roger Penrose's original theorem to cosmological settings, believes this is utter nonsense.
The physics is the servant, not the master.
Much like Yakir Aharonov, this is the professor's only ever podcast appearance. My name is Curt Jaimungal, and on this channel, I interview researchers regarding their theories of reality with rigor and technical depth. Today, we discuss top-down causation and why Ellis says reductionism is patently false. We also discuss his evolving block universe, what that has to do with free will, why there is no wave function of the universe, which is something Carlo Rovelli also says, and also we close with this legendary cosmologist's views on consciousness and why evil is a matter of fact, not opinion. Professor, what caused you to think about causation?
What caused me to think about causation? I started off in general relativity, where it's very, very simple. But I then got interested in biology, and my friend Dennis Noble and I spent a lot of time looking at biology. And biology is much more complicated than cosmology. Physiological systems are immensely complex. They have these many, many different levels, from the atomic level through atoms, small molecules, macromolecules, cells, tissues, physiological systems, and the system as a whole. And this is immensely complicated. Not only is it complicated in its structure, but in its dynamics. The way that an organism grows from a single cell into an adult is truly astonishing and immensely complex.
And what is causation?
What is causation? Causation is when you make a change. Either you make a physical change or you make it counterfactually, and then you find that reliably a specific outcome happens. So you do experiments and you measure what happens, and then the classic case is, apart from Galileo and dropping balls and that kind of stuff, the classic case is smoking causing lung cancer. And that has been the study of a lot of study, and it's completely reliably proven. And it's much, much more complicated than Galileo dropping a ball from the top of a tower. But in both cases, it's causation. Counterfactually, it happens if you don't actually make a change, but you can prove that the change would take place if the thing would happen if you did it. And so you can do all sorts of calculations in theoretical physics. Well, for instance, just a simple example, the spacecraft has just gone off and come back, and that was calculated beforehand, and then it happened exactly the way that they predicted it would.
You mentioned that in causation, that we have to intervene and then we're able to demonstrate that A caused B. But is intervention or an agent necessary for causation, or just necessary to determine that something was caused, but causation could have been there prior to an agent?
Causation is taking place all the time, and I could explain the different kinds of causation. There's physical causation, which is due to physical laws. There's causation when there's a purpose in it, and all of biology has purposes, every single living animal and technology. And so there's purposeful causation. Then there is a symbolic causation, and symbolic causation is what enables us to have language, to have society, and so on. And everything that we do, I'm speaking to you in a language, that's a symbol of what's happening. And symbolic causation is the basis of modern society. Then the next one is abstract causation, and abstract causation takes place when abstract things cause things. And this is the basis of computing. computing is symbolic, but it's also abstract. And you're using abstract symbols to calculate things. And then computers actually have agency. For instance, there are automatic landing systems in aircraft. There are factories which are controlled by computers. So it's not just human beings and animals that have agency. It's also computers have agency. And the final form of causation is social causation. And this is when in a society, people make decisions and they cause things that happen. Now, this is happening at this very moment in the war in Iran. People are making decisions and that's causing stuff to happen on the ground. But there's two very interesting further kinds of social causation. One is historical. And things that happened hundreds of years ago can cause things to happen today. And a classic example of that is the so-called Troubles in Northern Ireland, when things that happened 250 years ago caused people to be murdered in the present day. And the final one, which is very fascinating, is imaginative causation, is that at the present day, you imagine something that could exist, and then it comes into being. And Stephen Jobs is the classic case. He imagined the iPhone, and then everybody on Earth basically has got an iPhone. And that's a case of causation into the future because you have imagination. And that's the third form of social causation.
What is it about computer agency that differs from human agency, other than consciousness? Unless you also believe that current AI systems, for instance, have consciousness.
Well, no, computers don't have consciousness. They are symbolic systems. A computer is a symbol processing system because all programs are symbols. Algorithms are symbolic systems, and computers. They have agency because they can do things, as I've said, but they don't have free will. They do what they are told to do by whoever programmed them. So there's an algorithm. The algorithm is an abstract thing, and the computer is trained to step through the algorithm step by step, do whatever it says. And this is a classic case of what I think you've read me talk about. It's a case of top-down causation or downward causation. And computers are a very, very clear example because in computers there are what are called a tower of virtual machines. And this is the structure of virtual. And there's a physical one, and then there's an abstract one. On the abstract side, you have programs. And you have top-level programs, Fortran or whatever, Lisp, all sorts of things. Then you have machine code and an assembly language. So it chains down through a series of languages until you get to machine code, and that turns noughts and ones, and that turns transistors on and off, and then electric currents flow, and then it chains back up to produce the outcome at the top. So a computer is a very, very nice example of downward causation followed by upward causation. And the thing is that this is where reductionism comes in. The electrons flowing through transistors do not, they enable it to happen, but physics enables that to take place. But physics doesn't determine the outcome. It's the algorithm which determines the outcome. And so this is a classic case of an algorithm, in essence, telling electrons what to do.
Wouldn't someone like a Sean Carroll say, Professor Ellis, the Python example over here, which communicates to assembly code, which communicates to machine code, when we're saying that something happens at the Python level and it doesn't, or that has influence over the electron level, we're actually using a shorthand. We're calling it Python, but it's code in a different sense. It's code for electrons are doing so-and-so with semiconductors.
Yeah.
So if you actually look at what we mean, if someone was to say, well, what do you mean by thermostat? What do you mean by this and that causes so-and-so? We'll get down to some physical instantiation. And it's just physics in the end. That's the reductionist claim. All these, you made a decision to do so-and-so, it's because of your neurons, because of blah, 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 blah.
Well, if you say it's only physics, that's obviously false. If I tell you Maxwell's equations. Okay, here's Maxwell's equations. So what does that do? It doesn't do anything. I give you Newton's laws of motion. Tell me what Newton's laws of motion, of course, doesn't do anything. It only does something in a context, and the context is what decides what will happen. Physics by itself simply does not decide what happens. Physics enables it to happen, but it causes it to happen in the sense that it is told what to do, but the physics doesn't decide the outcome. The context decides the outcome. And now the thermostat is an extremely interesting example. Because the thermostat is a very simple system where you can see very clearly what happens, and it's a typical feedback system. You've got a sensor which determines the temperature. You've got a goal which you set on the thermostat. You would like the temperature to be 40 degrees, and it's actually 20. You determine the difference. And then that difference sends a current round to a heater. The heater heats it up, and that makes it up. So this is a classic example of feedback. Determine what it is, find the difference, and take corrective action to make it correct. Now, this is a case of top-down action because this is all at the macroscopic scale. At the microscopic scale, what happens is that by turning at the macro scale the dial on the thermostat, at the micro scale, you cause molecules to move fast. So that's top-down action. The physics isn't determining what those temperatures should be. It's you who are determining it by setting it on the dial. And so it's a classic case of top-down action. The physics is enabling it to happen. We are telling the physics what to do, and the physics does what we tell it to do. The physics isn't deciding anything. The physics is the servant, not the master.
I imagine a Sean Carroll, if I was to channel a Sean Carroll here, would say something like, firstly, you're a physical system. Now, of course, you can disagree with that, but all of what was just said would just still be accounted for by the microphysics, entailing the macrophysics. So that's, I imagine what Sean Carroll would say. I think he has an argument about that. I think you have arguments with him as well, but please, I'd like to hear.
The problem is very simple. Sean Carroll doesn't admit the downward causation takes place. No, that's simply wrong as a matter of fact. Downward causation does take place, and there's a variety of ways it takes place. It takes place by setting constraints on lower level variables, which many people have written about. And so a physical law would be of the form, a function of, a constraint is an equation of the form, a function of x equals a constant. And you change the constant, you change the constraint. Now, the very simplest one is a pendulum. And the pendulum, you've got a bob which swings, and the length of the bob determines on what orbit it is. And you can move it up and down, and you can get different rates of swinging. So that's a very simple constraint. The constraint is a macro-level thing. It determines what those micro-level particles that make up the bob do. And, of course, it's physics, but physics by itself enables it, but it's a technology that the physics is incorporated in, which decides what happens. And now the human brain is a very, very large hierarchical system, and it's a basic principle. Every very, very complex system is modular, hierarchical structure, and all of those words are important. And the clearest way you can see this is by talking to computer scientists, because computer scientists are the people who've actually built really, really complex systems. And they use those principles all of the time. So what the basic principle is, you've got a complex thing you want to do, and it's very, very complex, so you break it up into simpler things. And those are still very complex, so you break those into even simpler things, and you break them down until you have a very, very simple thing that can be done in a very simple way because it's now linear. And so then you then build those back up until you get the thing that you want to happen at the top. And so modular hierarchical structures, every living thing's a modular hierarchical structure. Every technological system, an aircraft, a motor car, the internet, they're all modular. Computer, they're all modular hierarchical structures. And if every biological thing is a modular. So the basic principle for constructing complexity is modular, hierarchical structures that are adaptive. And downward causation takes place in a couple of ways. One is by setting constraints, and another simple example is just an electric circuit with a battery and a light bulb and a switch. And you open the switch, you close the switch. And it allows the current to flow or it doesn't. And when the current flows, then electrons flow and so on. You are controlling what happens at the lower level. That's absolutely clearly top-down causation, no question about it. Now, the other way that top-down causation takes place is very interesting. Higher levels, you've got the higher levels made up of out of lower level entities. And what higher levels do in any complicated system is they create, modify, or destroy lower level elements. And that's the core of a huge amount of biology. Gene regulatory networks are there to create proteins. So the system as a whole, a gene regulatory network is a very complicated thing which reacts to high level conditions, and it is built in such a way that it will generate proteins. Modifying them takes place all the time. And the classic example of that is developmental biology, in which you have a set of cells, and they're all basically the same to start with. And then in the fruit fly, for example, at different places, signals get sent, positional signals, which tell different genetic circuits to turn on and off at different places. And that creates all of the body plan of a fly, a mouse, and a human being. It's where we get our backbone from. And so that is... And what happens there is cells are changing their structure. Cells start off pluripotent. They can become anything. But these processes turn cells into specific things, into blood cells, neurons, and so on and so on. And so things are created, they're modified, and they are destroyed. And apoptosis is programmed cell death. And for instance, when our hands are developing, initially they're all joined together, and then the cells between are destroyed, and that enables our fingers to be separate from each other. And so these are three different kinds of things that take place, and they take place in physics as well, and in organizations. These principles are extremely general. There's an organizational analogy for all of them. And the organization one is a very interesting one. An organization, let's say the Boeing Aircraft Company, is a huge modular hierarchical structure, very, very large. And what happens is, take, for example, the employees. There's a process for letting employees join the company, and you select who's going to join. That's the process of bringing in. Once they're members of the company, you train them. You train them into a specific task, and that means you're modifying them. By the time you've trained them, they're not the same as they were before you started training them. And then there's a process of assessment, and either they make the grade, in which case you keep them, or they don't, in which case you boot them out. And so this process of higher levels selecting what happens at lower levels, it happens in technology, it happens in biology, it happens in organizations. As I say, these are very, very general principles which apply across the board in truly complex systems. And there's not the slightest question that downward causation is taking place in any of these cases.
I subscribe to The Economist. Their science and their AI coverage is among the best I've found anywhere. And I say that as someone who reads plenty of it. I'll give you some examples. They just ran an analysis on how attitudes towards science are changing in American politics and what this means for research and funding in scientific institutions moving forward. This sort of high-quality reporting is fantastic. They even covered how dark energy may be weakening over time. Now, if that holds up, it completely changes our understanding of the universe's fate. If you watch this channel, those are exactly the kinds of questions that we explore every week. I subscribe to The Economist because their science and their AI reporting regularly surprises me with how deep it goes. And they're also, of course, known for global affairs, both political and economic reporting. They are top tier, and interestingly and flatteringly, Toe is one of the only podcasts that The Economist partners with. So as a listener, you get an exclusive 35% off. That's not a deal that they have just anywhere. Head to economist.com/TOE to subscribe. That's economist.com/TOE for 35% off. Okay, let's imagine we have a membrane here. And then let's say we have a salt ion over here. And then we say, well, what causes this to move from here to here? The physics story would say something about the voltage at this gate, or maybe the position of the momentum plus the voltage and the electric field and so on. That's the physics story. The neuroscientific story may be something about there are neurons over here and glial cells and modulators. And then the psychological angle would be, well, that's because we're going through grief and the world is filled with suffering. And then maybe the sociological one would say the electron moved from here to here because we're in this capitalistic system, this late stage capitalism and so on. All of these levels of explanation, are they all equally valid levels of explanation?
No. Okay. All right. Let me. First, I just want to talk about ion channels, and then I will talk about the different levels. And in terms of the huge discovery of molecular biology was that biomolecules are enormously complex and they change shape. And it's the change shape of biomolecules which causes things to happen at the molecular level. Now, in each of our neurons, there are voltage-gated ion channels which allow sodium and potassium to flow in and out of our neurons. And these are open and close according to the voltage across it. And so that is a case of controlling what happens in and out through the change of shape of these ion channels. And it's all perfectly understandable. Those are voltage-gated ion channels, and there are other ones as well. Now, the structure, the very important thing about the structure is that you're absolutely right. The brain, the central nervous system has a hierarchical structure, starting off with the brain as a whole, going down through neurons, going down through local networks, and then neurons and molecules and so on down to the bottom. And the principle which Dennis Noble and I insist on is that causation takes place at every emergent level. And the causation at every emergent level is necessary in order that the thing as a whole works. And so so you're thinking about something, you're feeling sad because someone died or whatever. That takes place at the integral level in the brain through circuits, probably oscillatory circuits in the brain. It takes place because there are action potential spike chains. Those are enabled by electrons and protons going, as we've just been discussing, and each of them is necessary for and right at the bottom level, it happens because protons and electrons are attracting each other. Every single level in this emergent system is needed in order that the thing as a whole works. And Dennis Noble, I think you've spoken to him.
Yes, I have.
He's done groundbreaking work on the heart. He's written a wonderful paper on the heart and the hierarchical structure of the heart and how it is pacemaker cells which control the pumping of the heart. And all the different levels are necessary for this to take place. And if we put this in a larger picture, we've got our physiological structures of our bodies with all these different levels. Well, why do they exist? They exist because evolution found it was necessary for them to exist. Otherwise, we wouldn't be able to function. So each level is there because evolution found it necessary for them to exist. And there are developmental systems which construct the whole thing up. And through this extraordinary procedure, because there are these three kinds of emergence. There's functional emergence, second by second, we're talking to each other. Developmental emergence, where we grow up over a period of 21 years from a single cell. And there's evolutionary emergence, which takes place over 100,000 years. And all of these three are integrated into each other. They each have created and allowed the other one to take place. And so this is a very, very complex thing that has taken place. It's taken place because of Darwin's theories of natural evolution, relative survival rates will determine what happens through these cases. And so the developmental systems are there to create each of these different levels, to create the proteins, to create the cells. And of course, cells are the first level in which all aspects of a living system take place. And then to tissues, and then the organs like the lungs, the heart, the eyes, and so on. And then the integral thing, us as a whole, and then society, because of course we don't exist on our own. We could not exist if we are our own. And it's a very important feature that in order to see this thing as a whole, you must include the society in which we live and the language by which we talk to each other.
I want to get to your work with Dennis Noble shortly and your biological relativity. Also, I'm super interested as to what you brought to the table, what he brought to the table, but we'll get to that. I have a question about these levels, an odd question. So there's an evolutionary level, maybe a societal, maybe a psychological and biochemical and so on and so forth. Is there something that's objective about these levels? Or is it that if there were aliens, they may have different levels, they may parse them out differently, almost like a preferred basis problem? Is there a preferred basis here? Because I imagine that the physicists would just say, look, even if there are aliens in other societies we haven't contacted, and they may parse out the world differently and come up with different explanatory levels, that if you keep asking them why enough, something they would agree on, if they all had science, would be physics. So that would be the commonality. Yes.
Look, okay, now I have written about the biology on other planets. So the first thing I insist on is that life on other planets will also be based in carbon. I think there's no question about that. Nothing else will do the job. And I know people have said maybe silicon, but no, it won't do the job. So it's because of this extraordinary structure of carbons, in particular, the way that proteins fold and control things. And it's truly extraordinary. That's the one thing. And the other thing is the way that a DNA can store information. And both of those are made possible by the structure of biology. So on other planets, I'm absolutely certain those would be the same. I'm also certain that an animal on another planet will have all of the same needs. The different physiological systems we have are there to meet needs. Like we have to be able to think, we have to be able to see if we're going to be able to survive. We have to be able to move. Underlying all of this is metabolism. Metabolism is one of the great things that we have to keep going. We have to take food in, we have to use it, change its form, get rid of it, and so the metabolic cycles are one of the great things. Then feedback control is another of the great principles, and this is happening all of the time. Feedback control is determining what happens with homeostasis, and the third thing happening all the time is adaptive selection. All of the time, no matter what we are adapting to the environment around us, and that happens mentally, it happens physically, it happens in all sorts of ways. So these are great principles of biology, and those will be the same on any planet. Now, they won't look the same necessarily. They may have 6 legs, 10 legs, whatever. That, in a sense, that's an irrelevant detail. But they will need to process information, or they're not going to survive. They will need to make decisions about what they're going to do in the future. In other words, their brains must be able to look at possibilities, decide what's probably will happen, and make decisions of how to act. In other words, they will have agency. And so well, the question is, what would be called life? And this, of course, has been subject of a great deal of discussion. But and Michael Levin has just run a whole discussion about that. Of course, Michael is a wonderful biologist.
Right. Yes, I've spoken to him a few times as well.
But in any case, I don't think there's any point in saying this particular thing is life is the whole bundle of all of these things integrated and acting together.
Tell me about your work with Dennis Noble. How did that come about, and what is biological relativity? What did you bring to the table? What did he cause, etc.?
Well, I can't quite remember how it started, but we started talking together. I discovered his work. As he says very clearly in those two books of his, he started off as a total reductionist, and he suddenly discovered that things didn't work that way. And that came particularly, he was trying to discover the pacemaker. And his wonderful work on the heart, the pacemaker, he discovered that there was the pacemaker cell which was doing this. And incidentally, I've got a pacemaker. I'm alive because of a pacemaker. And things, so it became clear to him that things happen at those levels. And in fact, there's two different ways of looking at this. You can simply look at a university in a biology department, and you will find departments. There are departments that study each level, the departments of physics, of chemistry, of biochemistry. So academia has discovered that there are these levels, and each of them have got laws of what happens at that level. And that's because this is the fact. This is the way that things happen. At each level in our bodies, there are different kinds of things happening. But they're integrated into each other. And so the first question is, what are the levels? And the second is how they're integrated. And there's both upward and downward causation taking place in various kinds of ways. And I think I've indicated various ways that downward causation takes place.
So you just mentioned something super interesting about the laws at different levels.
Yeah.
And I know this is quite a nitty-gritty topic. And I've spoken to Barry Lauer and Eddie Chen just on this one topic for 2 hours. On this one topic question that I'm going to ask you, which you don't have 2 hours for. But do the laws of physics cause anything, or do they merely describe? So I'm sure you've heard this is the difference between human and non-human.
Yeah. Look, there's no question whatever that they describe it. And this was Galileo's discovery. Not just that they describe it, but that in most cases they can be discovered mathematically. And of course, that's one of the big puzzles, why they can be expressed mathematically. Do they cause them? That is a subtle philosophical question. And at a certain level, I don't mind what the answer is. They describe it very, very accurately. And so do they cause them or do they describe them? If they cause them, it feels, as a physicist, it feels to me that gravity causes things to happen. Electromagnetism causes things to happen. And I find that a very comfortable way to describe. And those are described by Newton's equations, Einstein's equations, Maxwell's equations, which happen to describe them. But they are our way of describing what happens out there in the world. And there's this marvelous fit of our mathematics to what actually happens out in the physical world. And then that goes through to the emergent structures of metabolism and thermodynamics and all of that, first law, second law, all of that. All of these are tested. And of course, in physics, there are these emergent level of laws, like thermodynamics is an emergent level. It's not a fundamental one, it's an emergent one. And my own way of thinking about it is that they are caused by they're caused by physical effects, which we can describe by those laws. I don't know if that would satisfy you as a philosopher. I'm not a philosopher. I'm a pragmatic physicist. But they are described very, very accurately and been tested millions and millions of times. And we rely on them all the time when in engineering. When we design aircraft, we design anything, we are relying on the fact that those laws of physics describe what happens extremely accurately.
You worked closely with Hawking and not closely with Penrose, but you worked in parallel with Penrose. And I'm going to get to questions about that, especially where you differ with Roger Penrose. But Jenny Wagner, who I've also had on this channel, mentioned that you went from cosmology, but you found cosmology boring after some time, and then you moved on to neuroscience.
Yeah.
I want to know, was she right?
No, I didn't find cosmology. I did a lot of work in cosmology, which I found it very interesting. But firstly, there's just a general philosophical statement. I believe one should change what one is doing after a while. I don't think you should keep doing this. I think you should change, do something different, learn something new. And it takes time, effort, and so on. But so I've actually written quite a few papers on neuroscience. I've written some books on neuroscience, and I think one should change it because it does get boring after a while, doing the same old thing all the time. But it's also because cosmology moved from being a very theoretical kind of thing, and which I find very interesting, to being a calculational thing and a statistical thing. And so there are these telescopes with vast amount of data, and I'm not interested in those statistics. I'm not interested in doing what I would call engineering cosmology. And so, and I'm not interested in doing incredibly detailed calculations. I like clear, short calculations which prove something. And I've taken part in quite a few of those. I worked in parallel with Roger, and I'm a great admirer of the work he's done in general relativity. He transformed the subject.
Tell me, what is it about Roger that you admire most? And where do you agree with him that most others may disagree with him? And then, okay, well, how about those two?
Roger is an incredibly creative person, and his work on gravitational topological structure, gravitation and black holes was absolutely transformative. And it laid the foundation for the book that Stephen and I wrote called The Large-Scale Structure of Space-Time. Roger has gone on to talk about the brain and to talk about conformal cyclic cosmology. And I don't agree with him in either case. And he's also talked about quantum physics, where I half agree with him. I've also written on quantum theory. No, I don't believe in his gravitational wave function collapse. I think that's simply wrong. And I could explain it to you, but I mean, the basic reason is very simple. And then he suggests that consciousness is based on what happens in microtubules. It's simply the wrong scale. Consciousness is based on what happens in the brain as a whole. These circuits at the whole of the integral brain, and I've talked with a lot of serious brain people, and Roger's suggestion that it happens at the scale of microtubules, that's not the scale where consciousness happens. It's simply, from my viewpoint, simply wrong. I agree with him about the problem of entropy at the beginning of the universe. I think he's got a very, very valid point, that inflation is supposed to solve the problem of smoothness at the beginning. It doesn't. Inflation assumes that the universe is smooth before it ever gets going. And I think Roger's completely correct on that. Where I don't agree with him is conformal cyclic cosmology. And it's a brilliant idea, just in parallel, in a sense, with Stephen's idea of the no wave function, the no boundary proposal. In Roger's case, he doesn't actually, as far as I can see, have a mechanism from transforming from one eon to the next eon, and I don't think he has a mechanism. And the problem here is he talks about infinity, and Roger Penrose's conformal diagrams, you can look at infinity and you can see it there, but what that forgets, and I've written a paper about this, is that infinity is not a very large number. Infinity is larger than any number that exists. And a lot of physics confuses that. And so Roger has an eon and a connection in another one. And he says you get events happening here, they send signals to the boundary, and the signals come through. Well, the problem is he uses the symbol for infinity. If it actually is infinity, then any event down here gets diluted an infinite amount, literally an infinite amount, and the amount which gets transferred from this eon to the next is precisely zero. There is no way, if it's actually infinite, that a finite amount of information could go from this eon to that one. And to me, this is a conundrum which he hasn't sorted out, and it just doesn't work for me.
When I'm wrestling with a guest's argument about, say, the hard problem of consciousness or quantum foundations, I refuse to let even a scintilla of confusion remain unexamined. Claude is my thinking partner here. Actually, they just released something major, which is Claude Opus 4.6, a state-of-the-art model. Claude is the AI for minds that don't stop at good enough. It's the collaborator that actually understands your entire workflow, thinks with you, not for you. Whether you're debugging code at midnight or strategizing your next business move, Claude extends your thinking to tackle problems that matter to you. I use Claude actually live right here during this interview with Eva Miranda. That's actually a feature called Artifacts, and none of the other LLM providers have something that even comes close to rivaling it. Claude handles, inter alia, technical philosophy, mathematical rigor, and deep research synthesis, all without producing slovenly reasoning. The responses are decorous, precise, well-structured, never sycophantic, unlike some other models. And it doesn't just hand me the answers. The way that I've prompted it is that it helps me think through problems. Ready to tackle bigger problems? Get started with Claude today at claude.ai/theories of everything. That's claude.ai/theories of everything, and check out Claude Pro, which includes access to all of the features mentioned in today's episode. This video is sponsored by Shortform. If you want a free trial and an exclusive $50 off their annual plan, then go to the link in my description, shortform.com/TOE. If you're like me, you've encountered books that are so dense, finishing them is actually just the beginning. Shortform helps with that. Their book guides go far beyond pastiche summaries. They critique, they add context, they include interactive exercises, and connect ideas across authors. Take Gödel Escher Bach or The Master and His Emissary, two of the most demanding reads in consciousness studies on the popular market. My method is I read the guide first, then the book, then I read the guide again. So it's a triptych of engagement that cements understanding, better understanding for me. The GEB guide maps recursive structures in a way that exhibits intellectual pleiotropy, where one insight branches into consciousness, computation, and self-reference simultaneously. Shortform covers philosophy, science, and psychology, ipso facto, the intellectual core of this channel. They publish new guides weekly, and subscribers vote on what books get covered next. Their browser extension, Shortform AI, summarizes articles and YouTube videos with a single click. Go to shortform.com/TOE for a free trial and an exclusive $50 off your annual subscription. That's shortform.com/TOE. Can you spell out in detail what you mean when you say that physicists tend to misunderstand infinity as a shorthand for a large number?
Yeah, I wrote a little paper called The Physics of Infinity about this, and physicists tend to use infinity as a shorthand for a very large number. Now, infinity is not a very large number. It's bigger than any number which can possibly exist. And so to take an example, the universe is 13.7 billion years old. It's going to be... in another billion years, it's going to be 14 billion years old. Now, when will it be infinitely years old? And the answer is never. It will never be infinitely years old. No matter how old it is, it's not even the first step on the road to infinity, because infinity is bigger than any number that can possibly exist. It doesn't matter how long you wait, how far it goes. The universe, it is always in the future. It is always over there. I'm assuming, of course, that the universe will expand forever. I regard as highly implausible the idea is it's going to recollapse because the dark energy is far too large. I think it'll expand forever. It'll turn out to be what used to be called a heat death, which is a very strange name for something that gets colder and colder and colder. Things will decay, and baryons will decay, and there will just be this darkness left in the end. But it won't come to an end. It is never reaches the end, and that's the absolutely crucial point. And that's the problem with Roger's transitions between the eras. You never make the transition from this era to the next one if that symbol infinity means what it is supposed to mean.
Do you then not buy the physical relevance of ADS-CFT, so holographic dualities? And it doesn't need to be ADS-CFT. Many people will say, well, our universe is not anti. Okay, there are de Sitter CFTs anyhow. So do you find it dubious because they rely on some infinity, whether it's space-like or time-like?
Well, there's a couple of things to say on that. Firstly, the trouble with ADS-CFT is it obviously doesn't describe the real universe because anti-de Sitter space has a negative cosmological constant. Now, if the dark energy is a positive logical constant, it's causative. So that by itself proves ADF-CT is a load of bullshit. It doesn't apply to the real universe. That's the first point. The second point is that the idea of holography, of course, is a very, very old idea. In real world holography, not ADS-CFT, is a wonderful thing which you can do tests in a laboratory. But in general relativity, it's what we call the null initial value problem. And basically this, which Ray Sachs and various other people did in the 1970s. You've got a null cone in general relativity. You put data on the null cone. That is a three-dimensional surface. And the interior of the null cone is four-dimensional. And it's a mathematical theorem that what is the data on the three-dimensional surface determines what happens in the four-dimensional surface. That's the null initial value problem. And then, I actually wrote a paper about this with some colleagues and the real holography is the fact that a three-dimensional surface in general relativity, data on a three-dimensional surface determines what happens in a four-dimensional space-time. That's the genuine theory of holography as pertains to general relativity. It also pertains to electromagnetism in a space-time. The data, three-dimensional boundary, the data determines what happens in the interior. Nothing to do with ADA, with anti-de Sitter space-time.
Do you have thoughts on the mind-body problem?
Yeah, I'm a dualist. And I think it's actually very interesting to compare with digital computers. The mind. Look, the first point is that we obviously know that the mind is enabled to work by action potential spike chains traveling through and by resonant circuits. We know all of that is taking place. We haven't got the slightest idea how that actually leads to consciousness. We don't even have the beginning. Now, this is, of course, called the hard problem of consciousness. And the strange thing is some people try to deny there's a hard problem. Well, there is a hard problem. That's a simple fact. We have no idea how I happen to be seeing you, how we taste a grape, how we feel pain and all of that. We simply don't know at all how that happens. It's enabled by the brain. What we do know is that the mind can think of things, it can plan, it take decisions, and I would certainly insist that it has free will, and that's a whole nother discussion which we could go into. We certainly have agency, and I'd like to give you a little short story about agency.
Please.
This is a story which comes from Philip Ball, who's a wonderful science writer. So a very long time ago, the Leaning Tower of Pisa, Aristotle met Galileo at the top of the Leaning Tower of Pisa. And Galileo said, gravity works like this. I've got a heavy ball and a light ball, and I'm going to drop them and they fall. They hit the ground at the same time. And Galileo says to Aristotle, everything is subject to the law of gravity. There's nothing you can do about it. Everything will do exactly like that. So then Aristotle says, watch this. He holds out a pigeon and he drops the pigeon, and the pigeon flies onto a neighboring roof. And he says, you see what happened there? Gravity is there. The pigeon didn't want to fall, and so it didn't fall. And it was able to do so because it has all of the structure of the wings and all of that, which evolution has led to, because that helps pigeons to survive. But this is the whole thing about emergence. The fact that you've got those forces acting, the outcome depends on physiological structures which shape what those forces lead to. They channel causation in upward and downwards ways. And in particular, the pigeon decides it wants to land on the roof over there. It looks at the roof. It basically computes how it must fly to land there. It does that. And it does that. Incidentally, I think birds are incredible. I think the way they fly, they land, they plan, I think they're amazing. And it comes back to this thing also that in each there are these three different things. There's functional causation, which is what happens second by second. The bird there's developmental, and the baby bird has to learn how to fly. That's the developmental process, and that's an amazing thing that happens. The bird, they learn rapidly. And then there's the evolutionary thing that evolution learned it's a good idea for some animals to be able to fly up to get out of the way of predators. So all of these three scales always come in, and they always work in concert with each other. Evolution, and this is something that Dennis Noble has emphasized very, very strongly, is that ordinary evolutionary theorists, that many of them focus purely on molecules. Well, molecules is only a tiny fraction of what's going on. Physiology is crucial to evolution, and Darwin knew that. Darwin's finches, they survived differently on different islands because they had different shaped beaks, because that enabled them to eat different fruit. Physiology was what was Darwin's finches were about, different physiology. So physiology is central to evolution, which Dennis Noble has been pointing out.
And what does this have to do with consciousness? Are you just saying that ordinarily we think that there's some interaction problem, but you're saying, no, we can have something in concert that still is distinct?
Look, consciousness enables symbolism and enables humans to conquer the earth. So, this is the issue in evolution of levels of selection. And there's this whole debate in evolution: does selection take place at the level of animals or of groups? And sometimes selection takes place because if you've got a group of animals that can run faster or they're stronger or whatever, then they're going to win. But if you have a group of animals who cooperate with each other, they can do things which individuals can't do. And then particularly if they can talk with each other, they can plan what they're going to do, and they can plan technology, and they can plan, you're going to go around to the left, I'll go around to the right, and we'll catch them by surprise from behind and all that sort of thing. And so consciousness and the ability to plan gives you a huge leg up in the evolutionary race, and that's why human beings have conquered the earth. And we control all the other animals. And of course, we're destroying the earth because we're stupid, but that's another different part of the story.
I'm going to be speaking to Richard Dawkins soon, and I'm wondering if you have any questions to pose to him that you think he won't be able to answer.
Well, I would like to know if he has come to reconsider his statement that genes are replicators, because as far as I'm concerned, that is simply a false biological statement. You can put DNA in a petri dish, you give it all of the stuff he needs to create new DNA or to create proteins or whatever, absolutely nothing will happen. DNA is, as a simple matter of biological fact, not a replicator. The replicators are cells. And there's an important thing about cells. They replicate everything. They replicate DNA. They replicate a lot more than DNA. And I think that's something which is simply not stated clearly enough. Dennis, of course, knows this. When you replicate the cell, you replicate all of the organelles, you replicate the DNA, but you replicate massive other stuff, and that you replicate the metabolic systems, and those are not controlled by DNA. A lot of what happens in the cell, the metabolic structures, proteins aren't involved, and so DNA is not involved, and so that whole structure is simply, quite simply, not controlled by DNA. So there's a much bigger picture of biology than just DNA, and to look only at the level of genes is simply missing a vast amount of what's happening in biology.
This reminds me of your 2024 Foundations paper, where you had holism or biological holism. So are you saying that, look, if one was to say that the gene is what's being replicated, it's not exactly that, because in order for the gene to be replicated, you need some other context?
Yeah, you need the context of the cell as a whole. And one of the extraordinary things is the way when a cell splits, everything gets duplicated, and then the microtubules appear out of nowhere, and they organize everything. They push everything around. You create a new wall, and then the new cell has got a duplicate of everything which was in the old cell. Now that's quite extraordinary, and I'm not an expert on that at all, but I think it's a fascinating kind of thing. And these microtubules, they're like little angels which appear out of the out of the blue, organize everything, and then disappear again. And that's astonishing. Now, one other thing which I think is very important, and it's a slightly different tack, but I think it's important to say, is that it's very important to remember that the interior of cell is an incredibly chaotic place. It's the molecular chaos. There are billions of collisions a second taking place within the cell. It's not a quietly organized place where things happen in a very organized kind of way. There's a huge amount of chaos, the molecular storm, and molecular machines have been developed which extract energy out of the molecular storm. It's things like kinesin and dynein. And so that's an absolutely fascinating part of what goes in the cell. And to think that it's a very quiet thing where things take place on this in a highly regular, ordered place, this simply isn't the case at all.
Is the future open?
Yeah. No. This is part of the business of free will. But Stuart Kaufman, have you ever talked with Stuart Kaufman?
Yes, actually, yes. And I'll speak with him again in person. So the last time was over Zoom, but there were some connection issues. It's a great podcast. I'll place that on screen for people who want to watch.
The thing about it is to make clear that the future's open, it's interesting to go to technology, because technology, evolution takes place in all of those three processes take place in technology. There's developmental, there's functional, developmental, evolutionary processes taking place in technology. And my claim is the following. The major difference is in technology, there's nothing corresponding to DNA. And this is what Stuart Kaufman has emphasized. You can have an idea in technology, a completely new idea, which is completely unexpected. And that totally opens up completely new areas, which was simply not predictable. And the context I like to put this into is to think about what's happening in the universe as stuff happens in the context of the expanding universe, the Big Bang, nuclear synthesis, the last scattering surface, creation of galaxies, stars, and so on. And the question is the following. So I've got an iPhone. There's my iPhone. Mm-hmm. The question is the following. Was it inevitable that this iPhone would come into existence given the data on the last scattering surface? Now, I claim absolutely not. There is no way whatever that you could predict the iPhone would exist if you knew every single thing about the last scattering surface. And the point is the following. If you take, for instance, Jim Peeble's recent book about cosmology, it goes into all of everything which leads to the structures on the last scattering surface. We understand all of those processes in great detail. They lead to modulated Gaussian fluctuations on the last scattering surface. There's nothing on the last scattering surface which corresponds to a prescription that the iPhone will come into existence today. Nothing. And let's ignore all of the problems that make it impossible. Well, one of the things is, supposing there was such a date on the last scattering surface, how would it get into my mind? Is one of the things you could ask. But and that is a basically impossible task, for which I could explain in depth. But the deeper question is the following. So let's forget all of the problems. We're going to insist that what happens today was uniquely determined by what happened in the last scattering surface, because, or if you like, at the beginning of inflation, I don't care, whenever you like to say. The question is the following. Who wrote the nature of the iPhone into the last scattering? How did that get in there? And you end up with having to assume that there was some kind of I don't know what the phrase is, something not physical, something with intelligence wrote that data into the last scattering. That's what you have to assume. If you're going to assume that the existence of the iPhone in my hand today is uniquely determined. And that by itself proves that what happens today is not uniquely determined. And it's basically also as a part of the way of seeing that we have free will, because when Steve Jobs designed the iPhone, he thought of many different possibilities for the iPhone. He tried many different ones. The people who designed the transistors did, and all the rest of it. And this is the product of thoughtful, intelligent design. And that's what led to it. And it is not predicted by what was in the early universe. It's predicted by the fact that evolution, that the universe allows evolution to take place by setting the conditions for evolution. Evolution produces eventually human beings. Human beings have intelligence and free will. They design and build things like iPhones, computers, and all the rest. And that's the only story which makes sense to me as a way of understanding how the present-day world comes into existence.
Strick-Hoffman has his adjacent possibilities, and you have your possibility space work. Those, to me, sound like you're both approaching the same issue from different sides.
Yeah. No, he had the adjacent possible, but his recent work, he emphasizes that in technology space, the adjacent possible is not continuous. You can make a sudden leap into some completely different place. So, for instance, the CAT scanner didn't exist. The CAT scanner didn't develop as an adjacent possible to previous things like CAT scanners. It was, and the same as to, it was a sudden revelation that you could have a CAT scanner, which was not an adjacent possible. So Stu's basic point that he's making nowadays is that the thing that is different, evolution takes place in technology, but it doesn't have to take place. It can jump. It can jump to completely different places. And the same is true of the laser. The laser was a conceptual jump into a completely new part of possibility space which simply hadn't been explored before.
Now, I imagine you have a response to this that occurs to the standard physicist, which is that, okay, we can say that the last scattering surface that we cannot predict, so let's not use the word predict because then you have to think of the predictor, and that person or thing will have incomplete information. Okay, but that's different than saying that the initial conditions of the Big Bang or what have you, plus the laws of physics, entailed the iPhone, entailed the CAT scanner. Do you disagree with that?
They certainly don't entail them. They allow them, they don't entail them. Now, if you insist on saying they entail them, so I'll write you down Maxwell's equations, Dirac equation. Deduce for me from those how a digital computer works. You can't do it. It's patent nonsense. And if you really insist on it, what you're assuming, it's a form of intelligent design. It's assuming that there was some kind of thing which wrote that in and made it happen. It's basically a nerd's form of intelligent design.
I'm showing Maxwell's equations on screen or on a piece of paper and then saying, okay, how does a computer work? How does this and that work? There's a difference between some sort of pragmatic entailment that we can deduce it versus some ontological entailment that it is produced or it is entailed.
Well, if you want to believe in fairy tales, fine, go ahead.
Does your anti-reductionism imply your dualism, or does your dualism lead you to anti-reductionism, or are those to be teased apart? Are those independent conclusions?
Look, reduction and emergence both take place. The problem is when people claim that only reduction takes place. They both take place. I'm not against reduction. I'm against reduction as a philosophy being the only thing that happens, and to me that's quite obviously wrong. And just a simple example, which I've written about, deduce from a physics Darwin's theory of evolution. Okay, deduce from physics. should be able to do it if physics entails everything. The reason you can't is because physics does not have a concept of living or death. Darwin's theory of evolution depends on the concept of things being alive. Pick any physics textbook and you will not find in a physics textbook a definition of life. It's not part of physics. It's part of an emergent topic, namely biology. Life exists in emergent context of biology. It does not exist in a purely physical context. It doesn't exist in a technological context.
What if AI designs better spectacles than us?
Well, I am not an expert on AI. I do not claim to be that. A digital computer can do incredible things, but it does not have free will. It does what it's told to do. It does what the programmer tells it to do. Now, it does more than that. It can pick up new information from the outside world and react to that. It's a slight divergence, but what I need to emphasize in talking about all of this is the crucial fact that we are open systems. And the idea that you can predict, so let's go back to Laplace's demon, and I will know every single thing about every single molecule in this brain, your brain, at this moment. Okay? Now, as a matter of fact, that is not sufficient to determine what will happen in your brain 2 minutes from now. And the reason is because you're an open system. And this is a simple fact. Physicists tend to not think of context. They think in just generic terms, and they don't think of context. The fact that we are open systems means that new information, which we cannot predict, is coming in all the time. In the example I liked, there's a woman walking down the street, a car accident takes place. She's driving the car, an accident takes place. She didn't know the accident was going to take place. It takes place. Every single thing that happens in her brain from then on is different because the accident took place. And there's no way that you can predict that. Now, evolution has discovered that we are open systems, and so it's made our brains predictive processing systems. And this is where Carl Friston and all of that comes in. I believe that our brains are predictive processing. We are predictive processing systems precisely because we are open systems. It is for that reason that Laplace's demon cannot predict the future of our brains.
I also spoke to Carl Friston. Now, you keep mentioning people that I happen to speak to, and I want to know, is there anyone else that, since we seem to travel in the same circles, is there anyone else you think I should be speaking to regarding these topics?
The most important is Michael Levin.
Yes, I've spoken to him 4 or 5 times.
His stuff is truly amazing.
Yes.
Well, I think developmental biology in general is truly amazing. And people like Sean B. Carroll, the other Sean Carroll, have you talked with him?
No.
Okay, well, talk to the biologist Carroll, Sean B. Carroll. He's got this wonderful book. He talks about developmental systems and Hox genes and all of that kind of stuff. It's the bioelectricity of Michael Levin. To me, it's a completely unexpected. So there's the whole molecular stuff going on, and RNA, DNA, and all of that stuff, but he's proven conclusively there's another level going on of bioelectricity. And at first, this didn't even make sense to me, and I'm still trying to understand that. But he's proved conclusively that by his experiments that bioelectricity is at least as important as genetics in developmental processes. And much more than that, he's showed that there's apparent goal-directedness in some developmental process. They seem to know, and this I do not understand, they seem to know what the outcome ought to be. Now that goes against all standard, but if he can do experiments which shows that, then I've got to change my outlook. And that this is a project I will be trying to undergo in depth soon, because it's a revolutionary kind of thing, and it's Nobel Prize winning level stuff. If developmental processes in some sense have an image of where they're going, then development isn't what we thought it was, and I think that's an incredible thing.
Yes, actually, we both think the same. When I first interviewed him, the thumbnail that I placed on YouTube was the next Nobel Prize winner or something like that.
Yeah, I agree. I agree. Um, his work on salamanders and so on, where he can get them to grow second heads or whatever, it's amazing.
Yeah, what is it that's so revolutionary about his work? What is it that when you read his work, spoke to him, that it floored you?
Well, firstly, that there's a second level of control going on, which most people don't talk about. A standard developmental biology textbook simply doesn't talk about bioelectricity as being an important part of what's going on. That's the first point. But the second point is that appears to lead, and I'm speaking very carefully, it appears to lead to goal-directed developmental processes. They know what they ought to be. Now, that's quite different from standard ones, where we're very careful to say that the DNA isn't a plan of what will coming. It's a material used by developmental processes, and all of the magic comes from the Hox genes, the hierarchical structure of the Hox genes, which is what Sean B. Carroll talks about, and that kind of thing. But this is an area where I'm just finding my way, so I'm not going to say a great deal about it.
Can you explain about the standard argument for the block universe and then where you differ?
Yeah, the standard argument for the block universe is very simple. It's that in special relativity, you've got 4 dimensions and you've got your space-like, time-like surfaces. And when you change velocity, what seems space-like to you changes. So therefore, there are no preferred spatial sections in space-time. And therefore, we must have a block universe because there can't be any preferred spatial sections. Now, this is wrong in multiple ways. And the first point is that the big news is that special relativity doesn't describe the universe, general relativity does. Okay? So then what people say, but that makes it even worse because of general covariance. There are no preferred surfaces of time. And the answer is, this again is the problem of physicists who think in a context-free way. Put it in this context. Every cosmological model has preferred space sections. Every cosmological has preferred time sections. That's what standard Robertson-Walker cosmologies are. They've got preferred surfaces. T is constant, preferred timelines. And so they're simply ignoring the fact that in the real universe models, there are preferred time sections. And then the further point is what they're saying is completely at odds with what the Planck team does. And there's that canonical picture of the origin of the universe, last scattering surface. And the age of the universe is stated to be 13.87 billion years. So my model of the universe is an evolving block universe. In another billion years, that right-hand edge will have moved to the right a billion years. Space-time itself will have grown. Space-time will have got bigger. And so, how will that have happened? Well, through the Einstein field equations. And one of the things which is confusing is that the basic field equations of physics can be written in various ways, Lagrangian way, Hamiltonian way, but they can all be written in a way which is a time-dependent way. In the case of gravity, it's what's called the ADM equations, the Arnold-Taylor-Misner equations, and those write gravity as a space-time which evolves with time. So the standard, the real view, the real situation in the universe is that space-time is evolving. It started at the beginning, which was 13.87 billion years ago. At the moment, it's 13.87 years ago. It will be another billion years older in another time. The right-hand edge will have moved to the right. Now, the further very important point is this. This establishes a global direction of time. The direction of time passes from the beginning, which doesn't move, to the present day, which does move, and the present day is moving all the time. And there's this paradox that all of the important equations of physics are time symmetric. So where do local arrows of times come from? And the answer, which I've written about, is that the local arrows of time derive from the global direction of time. And one of the strange things is that at the present time, when people talk about the arrow of time, they only talk about the thermodynamic one and the second law of thermodynamics. But actually, there's an arrow of time for electrodynamics, for gravitational waves, for sound, for thermodynamics, for all of them. And one of the striking things is they all point in the same direction of time. And they all point in the same direction of time because they all derive from the same basis. The global direction of time breaks the time symmetry. So the field equation, the physics equations are all time symmetric. Their context is not time symmetric. And so this is what I mean by a lot of physicists who think about physics in a contextless way. When you put them in the context of the expanding universe, you solve the problem. We do not live in a block universe. We evolve in an evolving block universe. We get the direction of time because it derives from this expansion of the universe. And it's actually quite simple when you look at it in that way.
Didn't you also say that the quantum to classical transition is a problem for inflation?
Yes, that's also a problem. It's a great lacuna in standard theory is that in that picture they show you quantum fluctuations on the left. All of a sudden they're classical, and there's almost nobody who writes about how does the quantum become classical. And until you've actually made that clear, inflation is the way that inflation is supposed to lead to fluctuation in structure is an incomplete theory. And and now I've got a theory of, I agree with Roger Penrose that wave function collapse is real. And with my colleague Barbara Drossel, I've written papers about what we call contextual wave function collapse. And that wave function collapse is real, but the way it happens is always determined by the context. And we give a very detailed example of that in our paper called Contextual Wave Function Collapse.
So it's an objective collapse theory?
Yeah. And what that means is that essentially the Copenhagen interpretation is correct. And related to this is a further thing that I've written about is that people, and Sean Carroll in particular, they like to talk about the wave function of the universe, and that bases a lot of Sean Carroll's stuff about. He says the multiverse must happen because of well, this is obvious nonsense for the following reason. The Dirac equation and the Schrödinger equation are linear equations. Now, the real universe is not linear. So there's a paradox there. How does nonlinear stuff come out of a totally linear equation? And they try to say, well, it comes from the multiverse. Well, the real solution comes from looking back to general relativity. The great breakthrough in general relativity occurred when we discovered the concept of coordinate systems. You can't cover an ordinary space-time by a signal coordinate coordinate system. You have to have a whole atlas of coordinates, and it's the atlas which covers space-time, not a single one, and that's what enabled us to discover all the topological results in general relativity. Now, what I claim is exactly the same holds in quantum physics. There is no global wave function. That's a fantasy. There are local wave functions everywhere. And the local wave functions cover the whole space-time. But there is no single wave function for a universe, which completely undercuts the whole idea of the quantum multiverse. There's no wave function for a cat, all of that stuff. There's no wave function for a brain. And so the idea that one single wave function could encompass a whole brain is purely fantasy. It's obviously nonsense because the key fact of quantum physics, it's quantum physics equations are linear, and the Dirac and the Feynman path integral is based in the fact it's a linear operator on the wave function. The real physics is not linear, and the way to solve that is to have local wave functions which knot together to create nonlinear structures.
You think the multiverse is nonsense? Okay, there are various kinds of multiverses. So there's an Everettian multiverse, which
Yeah,
you've referenced. There's a Tegmarkian, like a
that's
mathematical universe.
well,
There
that's
is.
the one which tech marks one. The fact that something exists as a mathematics doesn't mean it exists physically, and it's just a simple misconception. I'm prepared to believe that some chaotic cosmologies will lead to different expanding universe domains. I'm prepared to believe that. I'm not an expert in inflationary theory. But the point from as a cosmologist, I'm a very conservative scientist. I believe that science is related to things which you can observe or which you can test. And in the case of the multiverse, you can't see them, you can't test them. That's because there are visual horizons. You can't see any further than a visual horizon. I can say anything I want to about it. You can say anything. Nobody can prove you're right. Nobody can prove I'm right. So I think you're talking metaphysics, not physics, when you say we're talking about those multiverses. Now, I know this is very unpopular with some of my colleagues, but I'm a very conservative scientist in that respect because and I have to be, because when I'm talking about all of this stuff about emergence, I have to make sure I'm on sound theoretical and experimental basis. And all of this emergence stuff is completely sound. And so I'm very careful to stick what I say to stuff which can be tested or observed. Now, of course, the problem with cosmology is that there's a uniqueness of the universe, which means we can't compare it with other universes. We can't rerun the universe, do tests on different universes. And that is, in a sense, the foundational problem. We only live in one universe, and we can only view it from one space-time point on one parcel icon. That's a basic problem in cosmology.
That's also part of my problem with fine-tuning arguments or anthropic principles, where they assume that there's some prior distribution, probability distribution on some constants. And then
Yeah,
you wonder, well, where are we selecting this from? All we have is one example.
yeah, yeah. You can imagine anything you like. I can imagine anything I like. We can see up to the visual horizon. We can be influenced by stuff up to the particle horizon. It could be, one of the interesting possibilities is space, that the universe could close up on itself on a scale bigger than the horizon, in which case it's definitely finite. One of the ones that I wished was the truth, but it doesn't seem to be so, is that the universe closed up on itself on a scale smaller than the visual horizon. And that's what I call a small universe. And in that case, you would see the same galaxies at different directions in the sky at different times in their history. And I think, as a philosopher, I would prefer the universe to be a small universe, because in that case, our observation relation to the universe is completely different than in every other case.
As you started to study consciousness and neuroscience, is there anything of the math from cosmology that applies or that breaks?
Now, I know people have, I don't think there's any relation. The brain has hierarchical structures, but it has columns, it has layers, it has different areas. It's nothing like cosmology. And I know some people have tried to make an analogy. I don't think there's anything there.
Sir, why are we here?
Okay, I've just finished a book which will shortly come out from Oxford University Press called How We Come to Be Almost Everything That Leads to Our Existence. And the last chapter is called Is There Meaning in the Universe? And then, of course, I quote Steven Weinberg saying, the more you know about the universe, the more pointless it looks. And to me, this is such a classic example of the tunnel vision of my theoretical physics colleagues. So he looks at particle colliders and he says, I can't see any meaning there. And you look at galaxies, you say, I can't see any meaning there. And you forget to look at your house, at your wife, at your home. You forget. You simply ignore all of the evidence from everyday life. So the question that I ask is, what should count as data about the universe? And the answer is telescopes, colliders, experiments, all of that. But in addition, all of everyday life is data about the nature of the universe, because we exist in the universe. And we are here. We are allowed to be here because the universe exists. And we have consciousness, we have free will. But the much more important thing, which I will finish off with, is that I am a moral realist. And I think this is incredibly important, particularly what's going on in the world at the present time. I think that there are some things which are good as a matter of fact, not as a matter of opinion. I think there are some things which are evil as a matter of fact, not as a matter of opinion. And so I would say there's a whole other thing I could go into, that what I call the deep structure of the cosmos's possibility spaces. There is a moral possibility space. And
interesting.
And so what is data about the universe? If you believe that moral realism is true, that is data about the nature of the universe. And you can try to explain in various ways why that is the case. If you don't believe in moral realism, then you think it's okay, the Holocaust was okay, you believe it's okay threatening to wipe out civilizations. As someone who has spent many decades fighting apartheid, fighting oppression in this country, I'm not prepared to believe that. I can't prove it, but I believe it is the nature of the universe at a deep level, and I believe that's a fundamentally important fact about the nature of the universe.
That the unprovability is a fundamentally important fact, or the moral objectiveness is an important fact?
The fact that that evil is moral is a fact. The fact that moral realism is true. Now, there's just one point that I must make clear, that I distinguish here between ethics and morality. Moral realism is what is actually good or evil. Ethics is what a particular society or person believes is good or evil. That varies with time, place, whatever. That is not absolute. It's the moral thing, the fact that threatening to wipe out an entire civilization is evil. To me, it is a crucial part of the nature of the universe that is a fact. And I can't prove it, but I believe it.
Sir, thank you for spending so much time with me.
Thank you.
It was an honor.
Okay.
Hi there, Curt here. If you'd like more content from Theories of Everything and the very best listening experience, then be sure to check out my Substack at curtjaimungal.org. Some of the top perks are that every week you get brand new episodes ahead of time. You also get bonus written content exclusively for our members. That's CurtJaimungal.org. You can also just search my name and the word Substack on Google. Since I started that Substack, it somehow already became number 2 in the science category. Now, Substack, for those who are unfamiliar, is like a newsletter, one that's beautifully formatted. There's zero spam. This is the best place to follow the content of this channel that isn't anywhere else. It's not on YouTube. It's not on Patreon. It's exclusive to the Substack. It's free. There are ways for you to support me on Substack if you want, and you'll get special bonuses if you do. Several people ask me, like, hey, Curt, you've spoken to so many people in the fields of theoretical physics, of philosophy, of consciousness. What are your thoughts, man? Well, while I remain impartial in interviews, this Substack is a way to peer into my present deliberations on these topics. And it's the perfect way to support me directly. CurtJaimungal.org, or search Curt Jaimungal Substack on Google. Oh, and I've received several messages, emails, and comments from professors and researchers saying that they recommend Theories of Everything to their students. That's fantastic. If you're a professor or a lecturer or what have you, and there's a particular standout episode that students can benefit from, or your friends, please do share. And of course, a huge thank you to our advertising sponsor, The Economist. Visit economist.com/toe, TOE, to get a massive discount on their annual subscription. I subscribe to The Economist, and you'll love it as well. Toe is actually the only podcast that they currently partner with, so it's a huge honor for me, and for you, you're getting an exclusive discount. That's economist.com/toe, TOE. And finally, you should know this podcast is on iTunes, it's on Spotify, it's on all the audio platforms. All you have to do is type in Theories of Everything and you'll find it. I know my last name is complicated, so maybe you don't want to type in Jaimungal, but you can type in Theories of Everything and you'll find it. Personally, I gain from rewatching lectures and podcasts. I also read in the comment that Toe listeners also gain from replaying. So how about instead you re-listen on one of those platforms like iTunes, Spotify, Google Podcasts, whatever podcast catcher you use. I'm there with you. Thank you for listening.